Look at the power consumption in a CMOS circuit. So a CMOS circuit is a complementary semiconductor circuit. So as you can see here, it consists of PMOS, or the pull up, and the pull down. So the energy consumption here, or the amount of power here, is actually dependent on the capacitive load. Okay, so the amount of capacitance here is very important. So the higher the capacitance, the higher the power consumed. Okay, now energy, also instantaneous power, is dependent on capacitance. So here, as you can see here in the first inverter, when it is pulled up, the higher power is produced when there is higher capacitive load. Okay, and if you have a smaller capacitive load, you will have low instantaneous power. Okay, and power can be described in a graph form, and as you can see here, power is actually the height of the curve. In terms of approach 1 and approach 2, approach 2 has lower power compared to approach 1 because the height, or the maximum amount of power, is lower. Okay, but in terms of energy, the energy is the same because energy is defined as power times delay. So energy is actually the area under the curve, and this approach 1 and approach 2 consumes the same energy because they have the same area under the curve. Okay, so now let's look at the matrix. So energy dissipation, if you have a device that causes a lot of energy dissipation, it will reduce the amount of battery life. So if you have a circuit that is very high switching, so it will reduce the battery life, and it also affects the packaging because if you have high switching, it will produce a lot of power, it will cause heating, so you have to alter the packaging to include heat dissipation packaging. Okay, as you know, energy dissipation is also described in the form of graph. So here, energy dissipation, if you have power versus time, this is the energy dissipation. But peak power is actually the peak value. So you can have a small energy, this has low energy but high instantaneous power, and this is known as the peak power. Okay, so the peak power affects the power ground wiring design. So if you have this kind of peak, it means that you have to put in better power and ground wiring to remove this kind of peaks, and these peaks can also cause signal distortion and affect the noise margin as well as the reliability analysis. Okay, so in a CMOS circuit, power can be categorized into 3 different types of power. One is dynamic power, which involves charging and discharging of capacitors. And the next power is short circuit current, the short circuit path between the supply rails during switching. And the last one is leakage. Leakage power is when the transistor, which is supposed to be off, is not actually turned off, so there is leakage or there is current leakage. Okay, so let's go to the first one, which is dynamic power consumption. Dynamic power consumption, the equation here is shown down here, which is CL multiplied by VDD squared multiplied by the switching frequency. Switching frequency is probability of the switching, which is probability for the circuit to switch from 0 to 1 multiplied by the frequency. So as you can see here, these three parameters, capacitance, VDD, and switching frequency, all affect the dynamic power. So if you have a high capacitive load, you will have high dynamic power. If you have very high switching, you will also have high dynamic power. As you can see here, it is not dependent on the size of the transistor. Okay, so the three parameters are capacitive load, VDD squared, and the switching. Okay, so energy is actually power times time, so you can expand it, you can integrate, and this can be simplified as CL multiplied by VDD squared. Okay, so now the next important point of the dynamic power is the transition probability or the switching activity. So let's look at this truth table. So this truth table is the truth table of a NOR cell. So you can take any cell here. So let's look here. If we look at the truth table, you can see for a NOR where you have one output 0 0 that produce a high, and the others produce a 0. Okay, so the probability of A equals to 1. Here it is 1, 2 out of 4, right, which can be simplified into 1 over 2, and the B is also 2 out of 4, right, so which can be also simplified into 1 out of 2. Okay, the probability of the output is 0 is 3 out of 4, and the probability the output is 1 out of 4. So here the probability transition from 0 to 1 is actually P out equals to 0 multiplied by P out equals to 1, which is actually 3 over 4 times 1 over 4. So it is actually 3 over 60. Okay, so now the C effective is actually the switching probability, which is 3 over 16 times the capacitive load. Okay, so now we can look, we found out what is the transition probability for the NOR gate. So you can also describe it in the formula form, right? So you can remember here that the switching activity in a CMOS circuit is for P0 to 1 is actually P0 times P1. Here is the formulas for all the basic gates, NOR, OR, NAND, and XOR. Okay, so now let's look at short circuit current, short circuit power. Short circuit power is related to short circuit current, which is actually the current that travels from VDD to ground here, or I short circuit. Okay, so this I short circuit is actually occurs during switching from when the transition goes from 0 to 1. There is a one small instant where there is a pass from VDD to ground. Okay, so this is known as the direct current path. So this is when both PMOS and NMOS are on. There is a small instant when both the transistors are on. Just when the PMOS is about to turn off and the NMOS is turning on, there is a one tiny instant where both PMOS and NMOS are on, and this creates a short circuit current from VDD to ground. So because of this, there is a short circuit current and there is a short circuit power consumption. So the short circuit power can be calculated using this formula, VDD times I short circuit times the transition probability from 0 to 1 plus the transition probability from 1 to 0. What about leakage power consumption? Leakage power is actually present when there is leakage from the gate to the drain or the gate to the source. Okay, so the most important leakage currents are the subthreshold leakage or I sub, and the next one is the gate oxide leakage. So the gate oxide leakage is actually the current that travels from between the gate to the drain and the gate to the source. In ideal situation, I gate is always 0, but in practical applications, I gate is not actually 0, and there is some tunneling or current that can pass through the gate to the drain and the gate through the source. That is because the silicon oxide is very thin, that the electrons can pass through from the gate to the drain and the gate to the source. Subthreshold leakage is actually the small amount of current that can go through, or the small current that passes from the drain to the source here when the voltage at the drain and source is below the threshold value. Transistor is not supposed to turn on or not supposed to create a channel at lower than threshold voltage, but here in this subthreshold region there is a small current that can still pass through before the gate forms or before the channel is inverted. So this is known as I subthreshold or the I leakage. So you can combine all these three equations for the dynamic power, short circuit power and leakage power, and this will form the total power that is consumed by a specific circuit. So as you can see here, the dominating power here is the dynamic power, and this comprises of 40 to 70% of the total power. And then the next one is the leakage power, and this can be 20 to 50% of the power consumption, and the smallest power is the short circuit power. So this is the decreasing power. So what is our main concern is the dynamic power and the leakage power. So we are always finding ways trying to reduce the dynamic power and leakage power, as this will affect our total power consumption tremendously.